We now want to discuss vectors on a manifold. To do that, first we recall that on xy plane, if we have a curve on xy plane like this, the tangent line at any point x0 is given by the following equation. And we are going to use this idea of a tangent line to define vectors on a manifold. Essentially what we'll do is that we will call these tangents as tangent vectors. That's the same thing we do in R2. And tangent vectors on a manifold will generalize this idea of a tangent line. To define a tangent vector, we first need a curve on a manifold. A curve, let's say C, from interval a to b to m, and some function on the manifold and for simplicity we are sticking to this sort of thing right now. Again, a and b, this ab thing is the open interval that will contain some t equals to 0. So let me note that down. A comma b contains some t equals to 0 where t is some sort of a parameter. And now we define the tangent vector. Now we define a tangent vector at C0 as the directional derivative of a function f of c of t. That means what I'm essentially doing is that I'm parameterizing the curve and then I'm picking up a point, and finally I am taking the tangent, or so to say the directional derivative, and calling that a tangent vector. So this f of c of t of a function along the curve, this is intuitive and understandable at this point, at t equals to 0. The rate of change of f of c of t at t equals to 0 along that curve will look something like this, which is just the directional derivative evaluated at t equals to 0. Okay? Now, in terms of the local coordinates, we write this thing as follows. Note that this is nothing but the chain rule in Rm, and these x means are your local coordinates. From this expression, what we can understand is that this derivative, this guy, this really means del of f composed with phi inverse 1 of x mu. Why? Because if you look at the following picture, this is my manifold M, and inside it there is some open chart U. This is the Rm. I have a point P over here, let's say, this phi takes p to x, right? Some x in Rm. So this phi inverse actually takes the elements of Rm to p. So we were using simpler notation, but if you in terms of the charts, this is how you write it. Okay, but we'll work with the simpler notation because that will make our work very easier. So again, we look at this expression. And from this expression, what we can think is that this rational derivative at t equals to 0 is obtained by applying a differential operator. Let's call the differential operator x. This is the differential operator we're talking about, which is denoted by x mu, del of x mu, where capital X mu is dx mu c of t with derivative with respect to the parameter. Applying this differential operator x on f, okay, so what I mean by that is that this means, or let's write it like this, the above statement means, let's denote the operation of x onto f as this. This means that x mu del f del x mu. Okay, this is what it means. And now let's see what happens if I take a very simple function. Let's say I want to apply this differential operator to a coordinate function. That means I want to apply this phi of c of t. I'm parameterizing the coordinate functions, but they just give me what? The local coordinates, right? So if I want to apply this on phi, this is just x mu del x mu. Sorry, let's not use mu, otherwise it will be a bit confusing. Let's use nu, and this is del x mu, because phi is just x of mu, so I'm writing x mu directly. Del x nu is just capital X of nu, delta mu nu. This is just x of mu. But x mu was what? It was just the derivative that was coming in terms of the parameter on the curve at t equals to 0. And one can interpret this thing as the muth component of a velocity if we consider t as something as the time. So this is how we define vectors on a manifold, through this differential operator. So the intuitive idea is something like this. If you want to skip all this mathematics, the intuitive idea is something like this, that if you have a curve on a manifold, you can take the directional derivative at some point, and the directional derivative is just the tangent vector on that curve. And this is how you can define a vector. But now you can do this analysis to all the points on the curve, and you get tons of vectors like that. And in fact, what one can do is that one can have families of curves, and from there, on those families of curves, on each point you can get a directional derivative and you can get a vector, and overall on the manifold, or so to say on every point of the manifold, you can have these tangent vectors, and overall you will get a vector field. That's how it works. Now let's get back to some other things, and this is going to help us to define something called a tangent space. So instead of analyzing one curve right now, we can introduce equivalence curve class of curves in M. So we want to introduce equivalence class of curves in M, and let's say C1 of t and C2 of t are two curves, and they will be equivalent to each other if they've satisfied the following conditions. The condition number 1 is that C1 of 0 equals to C2 of 0 equals to P. Then the point 2 is that at this point these derivatives of the both curves will agree. That means the velocity, or so to say the tangent vectors, will also agree as well. Okay, and these two curves will yield the same differential operator x at P. That means they will give rise to the same tangent vector at P. So if these two conditions are satisfied, we then write C1 of t is equivalent to C2 of t. And this is indeed, one can check that under these two conditions, this is indeed an equivalence relation, and we identify the tangent vector x with the equivalence class of curves given by these conditions. Okay, and when someone takes the equivalence classes of curves at P which belongs to M, namely all the tangent vectors at P, they form a vector space, and that space is called a tangent space. So I think I should draw it so that you can understand easily. Let's say this is manifold M. Okay, let's say this is one curve and this is a tangent vector. Oops. This is, let's say, curve 1. Curve 2 gives you another tangent vector. Curve 3 gives you another tangent vector. But all these curves have this point in common, and at the same time the tangent vector at this point is also the same. So you can draw many tangent vectors over there, and all of these tangent vectors lie in a plane. So let me draw the plane with a green color. This plane is called a tangent plane, and you can show that this tangent plane is a vector space as well. And we denote the tangent plane by Tp of M. This means a tangent plane at point P on a manifold M. To analyze this tangent space, we may use the theory of vector spaces as well. Also, since this tangent spaces contains our vectors, or that is introduced to us by this differential operator, if you compare this definition of a vector with the thing that you already know, that it has some components and some basis vectors, you can easily recognize that these differential operators are nothing but bases, and these are just components. We note that the dimension of the tangent space is equals to the dimension of the manifold. Why? Because if this manifold is m-dimensional, then these local coordinates are coming from this Rm, or Euclidean m-dimensional space. So you have m basis vectors. So your tangent space will also have a dimension m, which is equals to the dimension of the manifold itself. But note that this type of bases, note that the bases, let's call them E mu, that is denoted by this. By this I mean a collection of these things. These are called coordinate bases. Why? Because they're coming in terms of the local coordinates. But one thing you should also note is that by construction it is obvious that a vector x, this guy over here, exists without specifying the coordinate. It's just we are taking x and we are writing it in terms of some coordinates, just like points. And again, this coordinate is for our convenience only. Okay, and in fact it's not, it's this expression over here on the right side I just encircled right now is not unique as well, because if I take a manifold, I take a overlapping region, and there, let's say I have a point called P. So on this overlapping region I have some P. Let's say this is again UI UJ. P belongs to UI intersection UJ, and it's such that the local coordinates is given by, which is given by x, is coming from the local homeomorphism phi I of P, and let's say there are some local coordinates y, which is coming from phi j of P, right? Then at this point, if I have a vector capital X that belongs to this tangent space of P, I can write it as, let's say, capital X mu del X mu, like this, right? But I can also write it as, let's say, X nu del Y of nu, because this is a common intersecting point and these are my local homeomorphism that gives rise to the coordinates, or that helps me to assign the coordinates, right? So then, by applying a simple chain rule, we can see that this component over here, so let me use a tilde notation so that you don't get confused. These two components are related by the following. And this guy over here is nothing but the coordinate transformation matrix. And you can even prove it very formally as well. So this will be an exercise for you. Exercise. Let's call this expression A. Prove expression A. Alright. Now we were talking about bases. So one thing you do understand, is that the components are not unique, but the vector x itself is unique. So as we were talking about the basis, we said that we have these differential operators that we are calling a coordinate basis. Now the basis of this tangent space doesn't have to be necessarily my coordinate basis. In fact, I can do a coordinate transformation and change my basis as well. In general, any linear combination, so in general we can take a linear combination let's call that by some ei hat, and we denote it by a mu I, e of mu, where a mu I are components of A which belongs to some of A which belongs to GL of M R. This means the general linear group of M cross M matrices that have real entries and that they are invertible. So what we can do is that we can start with the coordinate bases and we can then rotate it. Okay, and this type of bases are called non-coordinate basis. We should note that most of the time we will stick to the coordinate bases, and it will be convenient for us most of the time unless otherwise stated.